Well, I will start presenting myself. I work here with air pollution for many years. And in the last years, we start to, including more than air pollution in our area of studies, we are trying also to involve some aspects of mobility, urban planning, some aspects of health impacts of air pollution. And I try to put all this background together in this presentation. And if you want, you can interrupt me and ask questions. It's okay. I think it's better. And I took some time to see that you come from different countries, different parts of the world. And it's very interesting because I know that you have different experiences that we can try to share. That I think will be very, very important. Well, I organized this presentation starting with one aspect that I consider that is very important. That is to relate the urban area and urban emissions in the context of climate change. Then to do this, we are going to start looking to the emissions of the cities. But these emissions of compounds will not be related to the green gases emissions, but also the other pollutants. And some data that I have related to the emissions, specifically to the South America, I'm going to present more. Mainly related to the ozone, methane, and particles that are these short-lived climate pollutants. I will explain this term for you. And if you have time, I have some aspects of health effects of air pollution and climate change and greenhouse gas emissions. But this is only if you have time, we are going to discuss these two topics because they are not so related to the main aspects of this presentation. Then when I was trying to organize this presentation, I thought that some questions could be important. It's not necessary to write, but only to think about the city of each one here. Because what we are going to discuss after will be related to these aspects. Some people here come from big cities like São Paulo, and it's very easy to see the importance of the city concerning the national level, like the population, size, gross domestic product. This is an index for economics. Do you think your city has importance in this national level? And then, do you have an idea about the growth of the population? For instance, we have here in São Paulo one very interesting aspect. The center of the city is not growing anymore, but the periphery is growing. And when we look to the distribution of the population age, we see that the youngest people are living in the periphery of the city. And also, we have all this population that live in the periphery of the city, they need to go to the center of the city to work. And then they have to spend hours, and also they have to spend hours in the public transportation, and this has a big impact concerning their living, their quality of living, but also concerning the emissions. And then when we have a city that is more spread, you have also to consider this. When the city is growing, but it's growing to the periphery, it's also going to impact more concerning time the people spend to go to work, to commuting, and also the emissions related to the use of transport system. And have you think about how your city impacts the climate? For instance, if it emits a lot of greenhouse gases, or if it emits a lot of other pollutants, no? Or concerning the kind of change in the soil use. And after thinking about this, then I know that we have here people from other countries in South America, Africa, Asia. That's very important. And then we have to think about the city can avoid the impacts of the extreme weather conditions or the extreme climate conditions like droughts, heat waves, how it can deal with this kind of threats to the city. And also, if the city is prepared for these extreme events, this aspect of resilience. I think when we think about these topics, it's easier to understand all other aspects that I'm going to show here related to this, concerning to these aspects. Well, I put here one thing that seems to be direct, that's the effect of the cities to the climate, and also what I think is even more important is that the cities are responsible for most of their emission, and then they are responsible for the climate change. But also the population that lives in the city are affected by these changes in the weather, changes in the climate. No? Then it's a process of changing and also being more affected by these aspects of climate change. There is a very nice picture from World Meteorological Organization. There is a group in the World Meteorological Organization that's the gourmet, related to the to aspects with the cities and the mega cities. Have you seen this already? No? I think this is a good overview of all the aspects. Usually, when we talk about climate change, we think about which pollutants we are thinking about. CO2, which more? Methane, yes, oxide of nitrogen and NO2O, water vapor. We are always thinking about these compounds that have a long life in the atmosphere, no? That stays for longer in the atmosphere. But I am going to show that other pollutants can have a very important aspect also. That is this local air pollution, that they are more related to the health effects. What I'm trying to show is that when we are controlling the pollution, we are not only helping to avoid health effects, but also it's going to help in the climate. We are going to see the effects of these pollutants also to the climate. But this is important because these pollutants can change here the formation of the clouds, because some of these that we call air pollutants, they are involved in the formation of the clouds, like the sulfate. It's a good example, nitrate, all these hygroscopic compounds. Also, we have the tropospheric ozone that's different from the stratospheric ozone. In the troposphere, it works as a heat absorbing radiation, infrared radiation. Also, we have, it's not pointed here, but we have the particles that we are, the aerosols and the black carbon that we are going also to see that have impacts on the climate. And not only this, but also we have all this change of the surface. When we have these cities, we have a lot of absorption of radiation, changing the albedo, changing creating these urban islands, no? Changing the wind configuration. All this, and when we consider the mega cities, they are very large and they're very spread, and then it can be very effective in changing all this configuration, the relation between the city and the circulation, the heat balance, and also the interaction with the clouds, precipitation, and the radiative process in the troposphere. For instance, here it's a picture of São Paulo. It's easy to show that with the size of the size of the buildings, all this configuration, it goes to affect the absorption of the heat it will be, we are going to have more heat than for the heating of the buildings, than the heat for changing the process of humidity, because we are going to have less absorption of water here. It's more drier. It's, well, another aspect is related to the social inequalities, because also for the exposure to the air pollution, we can see that it's not so democratic, the distribution of the pollution, because we are going to see when we analyze the data that we have places where the pollutions are higher, and usually distributed to the periphery also. But you see here, we have mixed kind of configuration. This is a vegetated area, or things like this. This is this poor houses that we have that's very frequent in the city, and most of these kind of configurations in the periphery. Well, we have all these that we have to take in consideration when we try to represent the emissions and also this heat balance in the atmosphere. Then this I try to put here. Then we have this change in the soil use and change in the energy balance. This is more related to the meteorological aspects. But also we have these two aspects that we are going to look in more detail. The pollutants, the urban pollutants, that we call these short-lived climate pollutants also, and the greenhouse gases. We usually, what we are used to do, we consider this one aspect, and this we consider another aspect. In general, groups that are trying to understand and to analyze the pollutants, they are not working with the greenhouse gases. No, it's usually we don't consider both together. But what we are going to see, if we are controlling this, we are controlling this, because the sources are the same. Most of the sources of these compounds are the sources of also these compounds. Some aspects of the relation between the greenhouse compounds, the relation of these compounds with the radiative process, also we have here the same aspects that can be considered. Then we have to not only to analyze this, but also to consider these other compounds when we are trying to study these aspects of climate change. Okay? I will show some details of these pollutants more at the end. Also, for those who are not used to this to these pollutants, that I think most are more used to consider the emissions of the greenhouse gases. No. Well, then why are the cities important? When we look globally, this is I will make all this presentation available, but some are without the reference. I will put the reference and then I will make it available. If you consider the cities and the power plants, the cities here is all the energy related to the transport sector mainly, and then the power plants. We will see that's the largest source of greenhouse gas emissions from human activity. They come from the cities. We had in 2010, more than half of the population is in the cities, and 7% of the carbon dioxide from fossil fuel are in the cities. And if we consider the 40 or the 50 largest cities together, they represent the 30 largest emitter of fossil fuel CO2 after China and the West. If we put together the 50 largest cities together, we are going to see the largest emitter after China and the West. In this this paper here that is analyzing the cities and the emissions of greenhouse gases, there are some aspects that are very interesting, and I included this phrase here. Cities are the most complex system created by the humankind. Is it true? No? Because we have a lot of, sometimes we have a lot of people, a lot of emissions, and also some of the emissions cannot be related in the city, but can be related to the production outside the city. No? But energy production for the people that are living in the cities. So the cities are responsible for 75% of the emissions in the world. Well, this I think we have everybody knows that now we are more or less half of the world population, a little bit bigger half of the world population living in cities, and by 2050, the estimative is that 70% of the population will be living in cities. Then this shows why it's so important to analyze the impacts of the climate change on this population, and also the emissions of the greenhouse gas by this population. Okay? It's okay until now? It's possible to understand? Okay. Well, this also, it comes from, there is some reference here that I put here from the United Nations. And another aspect that I think is very important, it's not only to look at the population and the total greenhouse gas emissions, for instance. Here it's interesting, they put the total of CO2 emissions, equivalent emissions by population, and here greenhouse emissions by GDP, gross domestic product. Then it's possible to see for some cities that we have, like here, for instance, Mumbai. I think now it's more than this, but 90 million inhabitants. But when we look the ratio between CO2 and population, it's a very low ratio because you have a lot of population. But if you look to the greenhouse by GDP, it's a high number, showing that you have a lot of greenhouses being emitted by some economic index. We have other cities that we have a lot of much more that are producing more because we have more gross domestic product, but less greenhouse gas per GDP, showing that the population is living better and emitting proportionally less greenhouse gases. But what's interesting, it's by population. Then we have very high places with low emissions like Mumbai, São Paulo. In total, the emissions are high, but the populations are high also. You see? If we, or another configuration like here in Japan, we have a high emissions per capita and a high emissions per GDP. Well, I put here, this is also from some references that are analyzing this C40 group cities. Here we have some cities that have a total high amount of carbon dioxide, but per capita emissions are low. São Paulo, Rio de Janeiro, this is in Brazil, Bogotá, Jakarta. Cities we have a high number of population and the per capita emissions is not so high. This makes us think that it's possible to grow and try to avoid a lot of emissions, but it has also to do with some different aspects, like climate. For instance, we don't need, here we need heating at home, but we don't have. You see, this is a very cold week, and it's very rare that people use heating for when we have cold days. But if you are in a city that you have to use heating, then you are going to have more impact on the emissions of CO2. It's easier not to have this kind of, for energy, for heating or for cooling. Yes. Is it okay? Yes. Yes.
What is the main difference between the reported total emissions between the cities? Is for the transport of the or because of the industry?
No, it depends. It's total emissions. It's energy emissions. Then you have when we consider energy, you consider transportation, and you consider also if you have like thermal power emissions related to thermal power, for instance, or other kind of emissions.
Yes, but you have here some cities that have the same size on population, but they have difference on the reported total emissions.
Yes, it's because of this. For instance, here in São Paulo, I was talking, we don't use energy for heating. Our energy comes from hydropower. Then we have less impact than a city that uses thermal power and use coal, for instance. You see, this makes a lot of difference. If you use cleaner energy, then your emissions will be less, will be not so high.
Hello, Professor. There is any? Could you tell us if there is any differences between South American cities, for example, Northern Hemisphere cities?
Yes, I'm going to show more details, but usually what happened in the North American cities, what we have that is very different. I'm going to show is this generation of energy. If you use a coal or if you use oil, it makes a much more impact in the emissions. Now in the United States, they are starting to use a lot of this shale gas. It has a lot of emissions of methane. Then it's going to have an increase in the participation of these greenhouse gases. When we go to Asia, for instance, in Asia we have a lot of coal for generating energy, and then you have this impact. You have also different kinds of preparing the food for cooking. The use of different kind of cooking is also a great impact on the emissions. For instance, if we go to some countries in South America or Africa or Asia, they use different kinds of cooking, like using coal or charcoal for cooking, then it's an impact. You have to analyze each one, and if you use like hydropower or for instance in Germany you see these small emissions because you use also nuclear power that's less impacting concerning the greenhouse emissions. No? Then you have to analyze each one. But the idea is that if you use cleaner energy, then you are going to have less impact. No? Also, if we look to the way the cities are changing, if you look to the cities or if you look to the country, the cities have this changing more faster than the countries concerning the emissions. When you compare the cities alone, when you compare the country, the cities are faster. And also, we had some meetings. One, it was the meeting in this meeting in Paris, and this is the last one in 2007. And many cities, mainly that cities from the C40, the group of cities in the C40, make an appointment to reduce the emissions, to have a reduction of emissions in average 25% by 2020. It can work or not. You know that the mayors were there and they signed a plan, but what determines if the cities are going to comply with this or not, if it's the economic situation. For instance, São Paulo was there and Rio was there, and they signed to reduction the emissions here in Brazil. But now, with this crisis, probably we are not going to to attend this target. Yeah. Also, we have this, the number of the mega cities is also expected to grow from 23 to 27 to 37 until 2025. That's also that is a question of concern. But one thing that is important is, okay, let me first show this. Here, when we put the total emissions, if we put the 50 largest cities together, they are the third emitter. The first is China, the second India, population, the emissions is here. United States and China, no, India is not here, it's in the last. And the third one is the 50 largest cities, and the four is this C40 cities that has this. I have the website of this C40 cities. I can show, but if I put here now, it takes a long to appear. No? Well, here is the gross domestic product. You see, if we put together the cities, the impact is very high. If they make some agreement to avoid the emissions, it's going to have a great impact here, you see, because this is 7 million tons for 2 and 2. And the participation is considerable here. If we have the cities trying to reduce, you are going to have an impact here. Well, the total emissions with considering this is no opposite, but total emissions including land use, change and forestry, and without land use. For some countries it makes a big difference when we consider the emissions also to land use and forestry. That's here involves the biomass burning and the soil use, like in Indonesia also. Well, here is this comparison between the total emissions, the population, and the GDP. The first here is China and the United States. When we have the population and we have the consideration of the economy, we are going to see the other slide shows when we make this, consider this total divided by the population and divided by the GDP, like that table. No? Here is the total from 90 to 2011, the percent of world total. We are going to see here that the United States was responsible for 16%, China 15%, and European Union 12%. Brazil is here is the 51, 1, 2, 3, 4, 5, the 51 with 5% of the emissions, but not here it's not related to the fossil fuel, but also including the land use and forestry, including the biomass burning. We hope that we will reduce this, but it was reducing, but the last years it seems that's increasing again the burning of forests. Well, this only two in the same data, but looking here, the differences between when we have only the emissions considering the energy, like this green, and the yellow is the total emissions. Considering the energy here relates to the fossil fuel and other ways of producing energy. That's the green. For Brazil, the main emissions are related to the total is more related to the soil, to the burning of biomass, and also Indonesia, also the burning of biomass responds for most of the emissions. For Brazil in total, not considering the cities, not considering São Paulo, but all the country, 75% of the emissions are related to the forestry, to the burning of forests. And in Indonesia is even more. And per capita, considering the population, we have Canada in the first place, United States, then the Russian, Japan, and Indonesia, European Union, Indonesia, China, and Brazil. Consider the total of the country. No? Here it includes the land use and land use change and forestry. Land use change is also changing the land for agricultural process, and also this is including biomass burning. One important aspect is when we look to all these pictures, I think most of you have already seen, not only for cities, but when it's related to other aspects, or even when considering the modeling, we're trying to model the climate change. Do you think, have you already think about the way these emissions are calculated? Because sometimes you see, the temperature will increase in some degrees if you consider a specific scenario, for instance. In these scenarios, you have the present situation, and then you make some estimative for the future. But do you know how these emissions inventory, they are built? Have you think about that? How we make the calculations of the inventory, the emissions inventory? It's not easy, and it has a lot of uncertainties. It's important that we think about this. When I am showing out these graphics, they are how the countries or how they are building this emissions inventory. Some come from global emissions. Some groups, we have many different groups that are trying to evaluate the emissions. But we always have to think about the uncertainties of the emissions. Because when we are trying to make these evaluations, we have here students that work with emissions inventory. It's not easy. When they say, no, the total emissions of CO2 by the transport sector is megatons per year, the total per year, it is an estimative based on the number of vehicles and based on the amount of fuel that each vehicle uses, and also the total of fuel that is burned in a country. But one thing that we must be careful is that this total, usually, they are made by some groups, as I said, but we don't have real measurements. We have measurements of air pollution data, these other pollutants. It's more, we have some data. But for the greenhouse gas, we have very few data. We have some satellite data, but local measurements, there are few measurements concerning the variation of CO2, the variation of methane, and other compounds. No? And one thing that is important is to build these inventories for each country. At some places, if we put here the place that have measurements of greenhouse gas, we are going to see some points in the North America and Europe. Now China is starting to have a database, but the others, we don't have measurements in the South Hemisphere, almost no measurements. We have no measurements. Here in Brazil, we have some measurements, but few. If we consider, for instance, Australia, they are measuring, they have a network for measuring, but I think it's very few points. Then in these uncertainties in the measurements, they may represent a risk to decision makers, because they have to decide where and when they can control the emissions, but if they don't know exactly which emissions and which are the main sources, it's difficult to establish the policies. No, don't you think so? Then this is the knowledge of the emissions emissions inventory is very important, not only for the mobile, for the transport sector, but for the energy. And also, another kind of uncertainty is the emissions related to this process of cooking, preparing the food. That is a great impact, mainly in areas of more poor areas. No? Do you know about this evaluation of the emissions inventory? Have you think about that? Have you thought about that already? It's really important. In the panel for the last panel for climate change, I think many people are going to talk these 2 weeks about the adaptation vulnerability, and they have this beautiful chart that's very interesting. And for each continent, they show the main impacts that can be for the physical system, biological system, and human and managed systems. Well, it's interesting because we have here representatives from each continent, I think, here, and each one has different aspects. But I put here one important aspect that's for the mega cities, because we are talking about these mega cities that are concentrated in coastal zones and can face the problem of the elevation. They have low elevation coastal zones, and they can have the problem of sea level rise and storm surges. Here we have in yellow is outside these low-level coastal zones, low elevation coastal zones, and in red is inside. Like here for Brazil, we have São Paulo and Rio. São Paulo is a mega city that's far from the coast, but Rio de Janeiro is just on the coast, and then it can suffer from the problem of the level, the rise of the sea level, like other cities all over the world. Then it's important that, as I said, if we have the main emissions from the mega cities, also the big cities are going to suffer with, for instance, sea level rise. That's one thing that is very difficult to avoid, and can oblige the population to move from the cities to look for another place. Here, if we look to the population, the fraction of the population, percent of the urban population in each country that would have to move because of the sea level, the rise of the sea level. In China is 20%. In Japan is 30% of the population. And if you go to other places, even worse, like in Bangladesh, in cities that are going to suffer with the rise of the sea level in our different places in the world. No? Well, I don't think we have people here from these places here. Well, now I'd like to go through more details related to not only the CO2 and other greenhouse gases. Well, I think we have all these numbers. We have the biggest countries, the biggest cities that are emitting. Also, we know that we have problems with the total emissions, with this emissions inventory. But I'd like to discuss with you other compounds, not only CO2, but also other compounds that are very related to the urban areas, like methane, that is a greenhouse gas, but it's also important in urban areas, ozone and the particles. I'd like to go through this because here, for instance, in this IPCC, the AR5, we have the compound that's directly emitted, but also we have, after these first emission, we have the compounds that are secondarily formed in the atmosphere and that can have some impact, some radiative impact. And looking here, we see this is clearly the impact of the CO2 directly. But when we look here, for instance, we have the first emission of methane. Methane has impact also. But also, when it goes to atmosphere, it produces the ozone. That also has some impact. This is the green. When we look to the halocarbons, they also produce ozone, other halocarbons, and they have this impact. Here the impact is opposite for the ozone because this is in the stratosphere. Here, if you have these compounds, CO, no methane hydrocarbons, VOCs or volatile organic compounds, NOx, all these compounds are emitted by burning of fuel for transport sector or also in power plants. When they go to the atmosphere, they produce the ozone that has some impacts, methane, and CO2. All these they have impact on the radiative process. You know. Then when we look to this, we are always looking to these compounds, but we cannot forget to also to pay attention to this one. And here, when we go to the particles, most of the particles, they are related to increasing the scattering, and for this they are related to the negative radiative forcing. But we have this kind of particles, black carbon, that is most carbon, elemental carbon, that's related to the heating of the system. Then we cannot only not consider the whole of the aerosols, the whole of the particles in this radiative forcing balance. It is very important. I'm going to show that some researchers are considering the black carbon as the second major contributor to heating after CO2. Then we have to look to this also. Okay, here. Have you seen this? This is more common, no? Yes.
Is the IPCC considering to adapt guidelines to include black carbon emissions in their inventories?
Yes, there are different initiatives to consider having inventories for black carbon and for the other pollutants. I am going to show some data here. Yes, it's now because there is one thing very interesting with black carbon that I'm going to show. It has the life in the atmosphere is much more shorter than the CO2, and then also to avoid the heating. If you take out the black carbon, you are going to see the effects much faster than when you stop emitting the CO2, because CO2 has a long life in the atmosphere, more than 100 years, and then it will take longer to note the impact of removing the CO2. But if you remove black carbon, now stop emitting black carbon, then it has a lifetime of less than 1 year, and then probably you are going to see the effect sooner than stopping emitting CO2. I'm showing this data. I put here only to define more clearly what we are calling these short-lived climate pollutants that we are also considering as air quality and pollutants, urban pollutants. Usually, these pollutants, they stay for weeks or months in the atmosphere. They are very different from the greenhouse gas that stay for centuries in the atmosphere. It's because of this that we consider this can do some climate change, because they stay longer and then they can be transported all over the world. These pollutants, they stay more closely to the place where they are emitted. But also in the atmosphere, they are going to suffer some changes, and some are going to stay longer in the atmosphere. But in the past, we considered this only to affect locally and regionally, more or less, regionally, and this to affect globally. Because do you have an idea how long does it take for a pollutant to go throughout the world? Do you have an idea of how long it takes if you emitted something here, how long it takes to go throughout the world? It's more than 1 year. First it goes in the same hemisphere, and then after longer time it goes to the other hemisphere. One good way of seeing this, it's looking to, for instance, that's very well documented, the emissions from the Pinatubo volcano. Then you see that it took more than 1 year to be all over the world. Then here is more or less the same of the other picture, only to show that if you have NOx, non-methane hydrocarbons, we are going to have ozone that's going to impact the climate. If we have the emissions of SO2, that's related to the burning of fossil fuels and coal and charcoal, we are going to the production of sulfate, and sulfate has impact in scattering the radiation and cooling the climate. When we go to the black carbon, it's going to heat the system. The emissions by the resuspension of the soil, or the best example is the Sahara dust. It's going to heat, to increase the scattering also, and then to the cooler the system, to have negative radiative forcing. Also, when we have production of clouds, and then we have the interaction of the aerosols with clouds, we have this process of decreasing the radiative forcing. This is also taken from the IPCC, showing the aerosols. Here we have that the pollutants and the greenhouse gases, they can change the short-wave radiation and the long-wave radiation. Some are related, for instance, aerosols are more related to the short-wave radiation because it's more related to the scattering of radiation from the sun. The clouds, depending on the type of clouds, we can have the interaction with short-wave radiation, scattering, or absorbing radiation, long-wave radiation, infrared radiation. Ozone also, it depends on if it is in the stratosphere or troposphere. If we consider the stratospheric ozone, we are going the interaction with the short-wave radiation, the more energetic ultraviolet radiation. But when we have ozone in the troposphere, it's going to interact with long-wave radiation, infrared radiation. It's because, depending on the compounds, it has some energy bands absorbing different energy. And then ozone can absorb in short and long-wave radiation. And the greenhouse gases and large aerosols and other kind of aerosols can interact with long-wave radiation. That's radiation that is emitted by the surface. No? And we have the short-wave radiation coming from the sun. All these compounds and also the changing of the surface make this balance of that we usually think about the balance in the top of the atmosphere between what's coming inside and what's going outside, and what's trapped. If we have more aerosols scattering, then we are not going to have, the heating will not be so high. But we have, if you not have the aerosols and are considering more greenhouse gas, then the balance will be more heating of the system, because more shortwave radiation will reach the surface and then will be trapped by the greenhouse gases. Then it's not easy to analyze the system because it's very complex. It includes not only the gas, but the clouds and also the surface. It's a process with all these aspects. I like this. Let me see if it works. Who has seen this? Who has seen this animation? I think many people already know. But I like this very much because this is not related to the emissions of greenhouse gas. We can see that it's also related because most of the process here, some process generate pollutants but also generate greenhouse gas. But most of the emissions, you see here, for instance, the green is organic and black carbon. The red one is dust. This more white is sulfate, and the blue is sea salt. Then all these compounds we classify not related to the climate change or greenhouse, but you see that they can go through different continents. It's not going to stay there in the same place that they are emitted. We can this is changing. When we have the season of the biomass burning, that's more in August, and it's going to increase the burning here, and then the emissions of organic and black carbon. Organic is basically the organic compounds. Here it's all particles, no? The dust, the effect of the dust is, you see the contribution even to the Central America from Sahara. Here some burning, the vegetation. Also in Australia, in the middle of Australia, the burning. And it's interesting to see the sulfate that is more in the north hemisphere is related to the production of energy with the burning of coal. Then we are going to see a lot of emissions of sulfates in China, Asia, and also of organic and black carbon. No? Yeah? A lot of emissions here. No? In Chile also, coming from that industries of copper. No? It's downloaded in site of NASA. It's not measuring. It's a combination of satellite data and modeling. And including these emissions inventory, it's based on modeling. But it's very interesting to see the circulation also. And I put this one, it's for ozone also, simulation of ozone. Ozone is, the other pollutants, they were primary pollutants, they were directly emitted. The sulfate, no, but it's fast, the production of sulfate from SO2. For ozone, no, ozone is produced by the hydrocarbons and the NOx. And then you see here that where we have more hydrocarbons and NOx, we have more the production of ozone. Also relates to the biomass burning because we have a lot of hydrocarbons emitted when we have the burning. But for ozone, the higher concentration is observed in the north hemisphere. This can have a great impact also. You see, you cannot say that this ozone that's produced by secondary process in the atmosphere will not interfere with the radiative process. You see that for some period of the year, like here in the north hemisphere, the highest concentrations are in the summertime when we have higher temperature. We have a lot of ozone that's going to interact with the radiation. Oh, well, I have shown some about the global emissions inventory, but I have shown the emissions for CO2. Now look into the other pollutants. I know this is not good. It was taken from the site of Edgar. It's a global inventory that's used mostly in this modeling, global modeling. They use the Edgar inventory when they don't have national inventory, for instance. It's global. And it's comparing different parts of the world. Here is for methane, SO2, hydrocarbons. This is methane. This is the other hydrocarbons that are not methane. CO, ammonia, and this is for NOx. What we see is that that's one important thing, that most the biggest emitters continue to be the same of the CO2, like Central and East Asia. Here it's for methane, then it have a contribution also from natural sources. But for SO2, we can see Central and East Asia also. For other compounds, more or less the same. The biggest emitters of the greenhouse gas are the biggest emitters of the other compounds. And then if we consider controlling the emissions of the greenhouse gas, it's going to be controlling the emissions of the other compounds. Here is for particles, PM10, PM2.5, black carbon, and organic carbon. I will show a little bit more about the particles and the difference between black carbon and organic carbon in the other slides. But here the same, we are going to see that we have South Asia, Central East Asia, being the biggest emitters for all these. We look here, they put together Africa and Middle East, the contributions. South America, for some compounds, the emissions are higher. I am going to show the emissions for Central. Here, Central and South America in this head here. The contributions are smaller than the others. I put here this author, Lamarck. He has many articles, papers considering the emissions, the global emissions. He works with another group that's the Gaines model for emissions. And I put here the total emissions. This is global emissions. You see, for some compounds, the emissions has decreased, like CO2, even for methane, they have the behavior for until 2000. I'm going to show more recent data. But some compounds are increasing until 2000. They have this increase in the concentration. But I put this here, it's not recent, to show the difference. Here is related to the biomass burning. The other was without biomass burning. This is with biomass burning. In the beginning of the 2000, it has a decrease in the contribution from the biomass burning, but from after 1950s, it increased a lot the emissions related to the biomass burning. It's very important to the contribution from forest and grassland from biomass burning in terms of total emissions. And this is another work from this International Institute for Applied System, that they made some estimatives for 2030 related to the emissions for different parts of the world, for different compounds, for these different short-lived compounds. For CO2, well, let me explain. Here is different places. And this in red, we have different scenarios, the old scenarios, no? And here the maximum feasible reduction. That's considering that it's going to reduction all the use of fuels. And then this will be this line here. And the other scenarios shows an increase in SO2, NOx, CO, and CH4. And most of this increase, it depends the different places. Like here, we are going to have the increase related to the fuels, for instance, NOx and SO2. CO is decreasing because most of the mobile sources are emitting less CO because of the control of the emissions in all the world. And here we expect to have an increase because of the, not only, but most because of the cattle, the agriculture process. It's going to have this increase in the CH4 emissions with time. You see more rapidly than the other compounds. Then we are going to look in more details the recent data related to CH4. This is going to explain what I'm trying to talk. This is the use of coal, oil, gas, and nuclear, biomass, and other renewables energy, like hydropower. It's here. This is the configuration for 1990, 2000, 2013. These are different scenarios, and for global energy demand, and 3 projections for 2030. These 2 scenarios here are scenarios that we are going to have. One is not controlling, the others are controlling the use of fuel, like explaining here. And then it's only to show what's going to increase. It's going to increase the use in these 2 scenarios of coal. Then we are going to have more emissions of greenhouse gas. And unless some 2 scenarios with the increase of renewable energy, it can be solar energy, wind energy, and hydropower energy, and also the use of biomass as energy. But what we are going to see is also for all these scenarios an increase in the demand for energy, for fuel to be used in energy. Different scenarios using different demands of increase. Nuclear power is also considered here in this scenario. But we are going to have an increase in the demand for energy in all these scenarios. I put also this is for energy and also biomass burning and the greenhouse gases, the emissions of greenhouse gas by biomass burning. We have here more or less an estimative an annual emissions of 2 gigatons of carbon. In the tropics, we have 8% of these emissions related to the biomass burning. Africa, 52%, South America, 15%. And it is divided in different phases. Flaming phases when we have the burning, exactly the burning, and also here when we have this phase that is not more with flaming, but is still hot, is still emitting. And it emits 90% of CO2, 90% CO in the total emission of when burning, and 1% of CH4 and other trace gas. This is also global emissions of fire, of carbon by fires in South America, Africa, and here a little in the Australia. this is from 2008 to 2010. We can see here, it's not a new reference. This is from one old reference. The counties in the satellite, Moody's satellite, the concentration of CO related to the burning, and the concentration of the increase of concentration of CO2 related to the burning. This was some data here. This is from 2010. It increased the emissions of CO2 because we had a severe drought in Amazonia. Then we have natural no, but we have usually burning, but it was even worse considering this drought in Amazonia. Then it increased the burning of the forest with the emissions. In the other IPCC, we had these scenarios, no A1B, A2, B1, and the new AR5, it changed the name of the scenarios. No, when we have RCP 2.6, is an increase in 2.6 watts per square meter. RCP 4.5, the increase in 4.5 watts per square meter. 6 is 6, and 8.5 is the highest increase in watts per square meter related to future scenarios. No? Is it okay? Then this is a comparison between from 50 to 2100 here, and the new scenarios, these climate modeling scenarios, they are also considered the paleoclimate data. No? And this is the radioactive force in total in watts per square meter. Then is the worst scenario, the increase in the highest. That's more or less compared to old scenarios that before, until the others IPCC. The new one, it's similar to this SRA2. We have A1B here. In general, what we are going to have is that the scenarios are spread between the worst scenario now and the best scenario, that's 2.6 now. It's involving all the other scenarios from the previous IPCC that we can compare. No? It's only to show that sometimes I am showing some data related to the old scenarios, but they are more or less involved in these new scenarios that are available for analysis. Then, although we sometimes show these scenarios from other IPCC, it can be compared to the new scenarios. They are involved here. Well, I'm going to show some emissions for South America. First, I'd like to, here is not possible to see, but this is the population. Look into the South America now. This is the surface area, and this is the density population. Then we are going to see that some places we have very, no, this is not only for South America, this is for more other cities, but I'm going to show after this for South America. The density, for instance, Cairo density population is very high when considered per square kilometers. São Paulo also, we have a high population. Oh no, sorry, the per square meter is not so high, it's very spread. We can see cities that are very spread because we have a high population, but when we divide it by the square meter, it's not so high. But like here in Mumbai, it's very high density population per square meter, Cairo also. And when we go here, here is the CO emissions, and CO emissions per square meter per year. Here is, the first one is emissions per year, total emissions, and we have emissions per square kilometer, e emissions per population, per capita per year. Then it's more or less similar when we look to CO2 also. CO2 is a greenhouse gas, but when we have the emission of CO2, usually we have the emission of CO. Because the burning of the fuel, the burning of even the biomass, what we have when we burn a fuel or a biomass, we have the emission of CO2, what we expect to have when we generate energy. We have to expect to have CO2, energy, and water for each hydrocarbon that is burning, no? Because it's a hydrocarbon, and then we include what when we are burning? Air, that's oxygen, and then we expect to have as the output CO2, energy, and water. This is the stoichiometric balance of the emissions. But what happens in real is that when we have the fuel, not all the fuel is burned, because it's not so stoichiometric. Then we have CO that's emitted. Also, not all the hydrocarbon is burned. Then some hydrocarbon is emitted without being burned. The same happens with NOx, because in the air we have nitrogen. This nitrogen goes through the burning process and then goes to the atmosphere. And then when we have CO2, we have also CO, hydrocarbons, and other compounds like sulfur, because the fuel has sulfur in its content. Coal has sulfur. And now we have all these emitted together to the atmosphere. Then when we compare this ratio of emissions of CO per population and per area, we are going to have the same similar profile of the CO2 with higher emission of CO and these emissions by square kilometer and per capita. We have, like here for Beijing, a high amount of emissions of CO and also a high amount of emissions of CO per capita, like the same as for CO2. And like here, I point here the cities that are from South America: São Paulo, Buenos Aires, and Rio de Janeiro. You asked about emissions inventory for these short-lived climate pollutants. There is an initiative from NEP under this Climate and Clean Air Coalition preparing a report for South America, Latin America, and the Caribbean. And what we have here, it's not the emissions. This is it's a global emissions performed with a model, emissions model. This is GAN's emissions model, evaluating the total emissions here, comparing different, also not only for South America, but here we have Latin America and Caribbean, and we have Asia and Pacific, North, South Asia and Pacific, Southwest and Central Asia, Africa, and North America and Europe. Put together the countries with high GDP together, North America and Europe, and Asia that we have here in red and yellow, in Latin America and Caribbean in green. The contributions of Latin America and Caribbean is higher in some compounds more related to agricultural process, like ammonia, and here it's CH4. Ammonia and CH4, the contributions are a little bit higher. And for other compounds like the organic compounds and SO2 and NOx, mainly SO2 and NOx, the biggest contribution comes from North America and Europe. Okay. Looking to the countries, Argentina, Brazil, Central America together, the countries in Central America, Colombia, Mexico, Bolivia. What we see here is the biggest emitter is Brazil and also Mexico. For instance, here we have CO2. You see, Brazil is the green and Mexico is the red one. For CO2, that's related to for Brazil, because it's all the countries biomass burning and energy. Mexico is more related to the energy, the big country. When we go to CH4, we have a big contribution from Venezuela. That's related to the petrol exploration, to the refineries. NH3 ammonia also, we have the biggest contribution from Brazil because of the land, because of the agricultural process, organic carbon, black carbon, and PM 2.5 also. This is relative contributions of the countries, but it includes the agricultural process, but not includes fires, vegetation, and forest fires here. If it includes, it will be even more the participation of Brazil, probably. Here it's for each kind of use. For instance, CO2 from power plants for sectorial emissions. Power plants and industry, mostly, and transport. This blue here is for transport. You see? The contribution from residential is smaller for CO2, but it's greater for oh my God, remember the name of the chlorofluorocarbons, thank you. And also for organic carbon, a lot of emissions from residential and also black carbon. That's related to the cooking process also, to the cleaning process for the organic carbon. But most of emissions also come here from, most no, but a great participation from the transport sector also here. Ammonia from agricultural process, no? NOx from the transport sector, SO2 from power plants, and PM 2.5, that's the fine particles, come from power plants, also residential, and also transport sector. Black carbon coming from transport sector and residential also. It's this kind of data. It's not related to the measurements, but it's related to this emissions inventory that has a lot of approximations to have these numbers, no? To reach these numbers. Okay? I know that there are people from other countries in Latin America, and I don't know if they agree, but then they can discuss more and see if they agree with these total emissions. And this because at some point this is modeling, and maybe and probably the people from each country has more information and can discuss more this data and the participation of each country in the total emissions. Like here, for instance, considering this. For each place, by sector, when we consider by sector here, the contribution for CH4, here is for CH4. We have Argentina being the biggest contributor for CH4, Bolivia, Brazil, Brazil is the highest, because the main here. See? No, Paraguay, yes, Paraguay, related to the agriculture process, okay? Then it's Paraguay is the highest participant. Well, if we try to analyze this data, probably someone is going to say, no, I don't agree with this kind of evaluation because it has a lot of differences between each country. No, it's not related to the total. For each country, the amount of, for instance, it's not related to the total, but for each country, how is the amount of, for instance, CH4 that comes from agriculture, that comes from waste, and that comes from coal, for instance, for each one. For instance, for Paraguay, most of CH4 come from agricultural process, okay? And a little participation of waste and residential. For Ecuador, most comes from coal and oil, and it's the same for Venezuela. Most of the emissions of CH4, methane, from Venezuela comes from coal, oil, and gas. This is the way we can see these graphics. For black carbon, I'm showing black carbon on CH4 because we are going to discuss more these compounds. We see for black carbon that in Argentina, most come from transport. It's the same here in Brazil and also in Venezuela. For Bolivia, we have a great participation of residential, also in Central America. For black carbon, it means that it's being used some kind of or charcoal or coal for burning, because here residential, most of the emissions in residential or is heating, or is for the heating system, like burning wood also, or for cooking, burning wood, burning charcoal or coal.
Maria?
Yes.
I have a question. In the previous slide, please.
Mm-hmm.
Could you turn back? We are discussing here because it's usual to, how can I say, present this kind of information in sectors, energy sector, transport sector.
Yeah.
In this case, coal, oil, and gas, it's double content. A content, I don't know.
No, because you say about it's the exploration of coal, oil, and gas, because you say about power plants, for instance, or other. No, it's power plants. You are going to have to use oil for power plants, and then they are all here. But the other use of and the exploration of coal, oil, and gas, it comes here.
Okay.
To product the coal, oil, and gas. It's not counting double, no, because here you have also this wood burning, and I said charcoal burning. This is in residential. This is for generating energy, and this is for producing these compounds, and the use of these compounds not in power plants or in the transport sector.
Okay. Thank you.
Yes, but I can see this more detailed. Yes. Mm-hmm. You see, it's not going to be the consideration of the burning, because the burning, it's going to increase the contribution of the black carbon. And the black carbon here, it is more related to transport and residential, not related to the burning here. It's more this is related to the production of these compounds. And they also have in this GANS model the estimative for 2050 for some compounds, like for SO2, the decrease, NOx an increase in the hydrocarbons, and CO a decrease, and after an increase, and ammonia an increase, and this considering different scenarios. Increase in the population, then we are going to have more population. It's going to be used more fuel, but also you see that NOx is increasing because you are using more fuel. But at the same time, the control for the emissions will be higher. For instance, in the transport sector, then the decrease in the emissions of CO, after some time, will increasing the number of cars, then the CO starts increasing again. This is related more to the agricultural process, then it's considering that it's going to increase with the number of area used for agricultural process. And the pollutants related to the burning first will decrease, like the CO, and then when the number of emitters, the mobile emission, for instance, then it's going to increase after a while. The total of, this is for the co-pollutants, these short-lived climate pollutants. For the greenhouse gas here, what's going to observe, they are CH4, like ammonia, related to the agricultural process, is increasing. CO2 is increasing because also the same reason that for NOx, the increase in the use of energy. And also it's increasing the use of halocarbons, considering this increase. This is also our estimatives. Then we must look at this with some, this is related, one is before 2000, no? And then decrease, all decrease. We have to take care because it's modeling data. This the same was made for all the countries to reach that total. This is estimative for other countries for each pollutant. I am including CH4 here because it's very important for the atmospheric chemistry. I'm going to show this after, some atmospheric chemistry when we stop and then start again. Here for Brazil, it's going to increase the emissions, the total emissions, and more related to the agricultural process, this increase. Also here we have this, from the exploration of coal, oil, and gas, we have to explore, even if gas or even if petrol, we have a lot of emissions of CH4 related to this exploration. And also with the waste, the production of CH4 related to the waste. Then these are three sectors that is increasing. For black carbon, again, residential combustion is not going to change. The transport sector is going to decrease, and after some time it's going to increase again with the number of vehicles. And for agriculture also increase, and then it's going to decrease, hoping that it's going to use less burning of vegetation in the agricultural process.
Okay. Hello?
Sorry. What are the assumptions of the scenarios?
Well, the assumptions here of the scenarios, I not put here. It is considering for each country the increase in the demand for energy, the increase in the population. It's not making and the implementation of control of the emissions. Like you have some control of the emissions that is being implemented in different places in different countries, then it's going to have this implementation of the emissions, the control of the emissions. But you consider also that the population is increasing and the demand for energy is increasing. But it's, no, it's in the beginning, it's considering that you are decreasing because you are implementing the regulations for the emissions. Like here in Brazil, we have a lot of regulations. But after some time, all these regulations stabilizes, and then you have the increasing in the number of vehicles, and then we start having increase in the emissions. You know, because then it's, here we have this, we have reached the smallest emissions per vehicle. And then what's happened now that the concentrations decrease. But after some time, we expect to have an increase again, because they are going to emit the same, and we are going to have more vehicles. And because of this, we have this behavior. First, some decrease, and then increase again. In the agricultural process, the same. It starts increasing at some point, but then we have no more burning, and then we expect to have a decrease related to the, because this is for the black carbon, related to the burning, and then we expect to have a decrease. It's not, it's a scenario, it's not like an optimistic scenario, but it's a scenario considering that's business as usual, demand, increasing the demand, but also using some control for the emissions.
Thank you, Prof. Thank you for the presentation. While you were showing us the clips, the short video clips, you showed us one with aerosol all over the continent. But the one I'm particularly interested in is the aspect of the African continent. The aerosol was so thick, and I wouldn't know why it was so, and I would like to know the implication it has on the agricultural sector for Africa.
You say the total amount of emissions of related to the agricultural process?
You showed us about two clips. There was one that you showed us that you said it's aerosol, and it was really light on South Africa and South America and America continent, but on Africa it was very thick. So I wouldn't know the implication it will have on agricultural sector in the continent.
What I am going to show, I think now we have a time for coffee, but I'm going to show more the impacts of the aerosols. I will stop showing these scenarios and going through these aspects of the aerosols. Different aerosols, they have different impacts on the radiative process. And we are going to see these impacts that are related to the burning, and also the aerosols that are more related to the scattering of the radiation. Yes, I think we are going to discuss more the aerosols. Oh, I am only, well, with these scenarios, it's going to show some implications for the formation of ozone impacted by this scenario. But I think we now have to stop for the coffee, and then when we return, I will go through these aspects of the aerosols in more detail, and also this chemistry of CH4 in the atmosphere. Okay? I think it's better to discuss these aspects.